let me start my discussion for today. So, of course, virtualization and cloud has been on everybody's last couple of years. We have had a lot of people talking about it. Most of us have tried it, are beginning to use it. Some have all actually built entire businesses around it. So it is a very, very important and looks like a major trend. And one aspect that comes up whenever we go to these kinds of systems is what kind of security impact it does have. Now, so generally if you look at how we are doing security in the real world today. So what if you are a bank today, right, and you're running online banking, what all are you doing? You think about it, you take all your servers, put a lot of firewalls ahead of it, application level gateways, whatever the best, latest product you can get on it. You put all sorts of antivirus tools on it, post-intrusion protection systems. There's a huge number of tools, but in the end what you're doing is some combination of a blacklist and a whitelist. These things are allowed to be run, these things are not allowed to be run, and then you have some mechanism for checking, right? And of course, at the application level, you start doing additional security, like all your transactions go over HTTPS, and then when you're sharing credit cards and other things, you put in some data protection mechanisms for protection. Right. So the sort of general approach is to use access control, some kind of blacklist and whitelist, right? And then sort of over the many years, what we have evolved from is a scenario where the access control was very, very coarse. If you are such an expert user, you can do anything, right? To getting far more fine-grained. Like what Adrian was saying, we don't even want the administrator to go mess with the keys. That's a valid concern because the way organizations work today, the admin or the guy who has root access is often a whole series of contractors that are coming in and out, even in very large organizations, or they have outsourced that activity. So the challenge is how do you try to do access control in a cloud setting where everything is far more open. So we have to think of or extend whatever techniques we have had, maybe look at different ways of doing it. That's where the challenge comes from. And one issue in all of this is the fact that the problem would be far, far simpler if we didn't have every application, every part of every operating system going through so many iterations of change. Like like today, I don't know, I'm sure everybody has this experience. You open up your device, whatever it is, and there is an update sitting for you every so often. And 99% of the updates don't add any useful functionality that you are ever going to use. Or at least, but still, because of various reasons and the way software deployment has to happen, this is something that needs to continue. And this poses a tremendous challenge to whatever security technique you deploy. You have to, if you are using antivirus, you keep updating your DAG files every so often and they keep getting bigger. Right? So, now when you come back to the cloud, and virtualization is a key component of at least I would say, though there are some like Google App Engine and things like that don't really use virtualization in the formal way because they abstract at the application layer, right? But the most common kind of usage, look at Amazon and a number of other places, is you first virtualize and then you offer a cloud delivery model on top. So it sort of goes together to some extent. So of course they are separate technologies. Now, virtualization, you have to go back and ask yourself what kind of security architecture you need. And virtualization actually spans three scenarios. You're just virtualizing your small server in your own office. You are a larger organization, you just do a private cloud, right? Or you're doing a multi-tenancy kind of thing all the way like what the big guys are doing. When you go to this larger scale, not only are there the normal challenges you would have, but there's the whole configuration control challenge. If you have set up 500 VMs over a dozen servers, and then set up virtual switches and sort of different VLANs and all of that over it, it's very risky that somewhere at some point in time, if somebody manages to create another additional rogue VM which you cannot track, or an additional port or opening to sort of some other part of the network which you assumed it was private and became public. So all of that part, though I will not spend too much time on it today, it's more a process thing. I don't know. It's very challenging to do configuration checks and configuration validity. It's like a tremendous problem in itself. But that, like if you're doing a cloud and if you don't worry about those things, you're definitely leaving a big hole there. And it's a major operational challenge. No? And then, of course, even the APIs you use to provision this, there are all sorts of man-in-the-middle attacks that could happen, or even, I'll talk a little bit about that. But I'll talk more about what you could do, both in terms of what kind of architecture and this thing. At least some things we have tried, I'll share with you. So just to review, so this is what a typical, single server virtualization environment looks like. Bunch of guest VMs, heterogeneous operating systems perhaps, a hypervisor, some hardware, and a management mechanism. Another thing that is at least much talked about, in many ways it's a regurgitation of thin clients, but this virtual desktop infrastructure is the idea that for very large organizations, if you're a large BPO with 30,000 employees, just managing all those desktops and securing all of them is a headache. So can't you just virtualize all of that, have all of it get run off servers in your sort of server farm, which is far easier to upgrade, manage, and protect. And so VDI has become sort of a model that is at least being tried, and it has its own challenges because people are trying to put literally hundreds of desktops on a mid-sized server and try to serve. And why is this a challenge? Well, the most obvious reason this is a challenge is that in current desktops, people have been willing to spend lots of CPU cycles on security, on the sort of just, if your typical desktop spends 30% of its time just doing scanning of different sorts, the typical user doesn't care because it doesn't seem to be, these are a few examples of vulnerabilities which can be exploited by the guest OS. So it's not sort of a remote network attack, but if you are running a guest on that same hypervisor, then you can escalate your privilege and get into the hypervisor, but which is a significant vulnerability. If you look at the management console, again, people have found lots of issues. I don't want me to go into the details of that, but sort of every major platform, somewhere or the other, you can find. It's just the size of the code becomes large. Management consoles, by their definitions, are also fairly rich in sort of APIs and things they create. So Finally, of course, if you're doing virtualization, there are attacks that can happen because if you're not using an IOMMU, which much of the hardware currently does not have, then there are issues with the DMA. And Adrian did point out one example of such a case. This is a more of pictorial representation. So on the API and browser vulnerabilities, sort of I already covered this and talked about it. Just to highlight, even browser plugins. So often what happens is if you have a large deployment of the cloud, if you have 500 VMs and you want a picture of it, seeing what's happening there, then you need a way to manage it. You need, for example, one thing people are using is browser plugins, and those plugins themselves can have vulnerabilities. So your browser gets, the plugin has a vulnerability through which misconfiguration can happen or malicious configuration can happen, which can take you sort of into a very insecure situation. Now, what I will talk more about now is a couple of possible ways you can leverage virtualization to also help. Right. So, you can, for example, the fact that, yes, the hypervisor is 300,000 lines of code, but it is a lot less than an operating system. So, it is the number of vulnerabilities you may find in that is an order of magnitude less. You can, for example, place whatever you have today as your security product, whether it is your firewall, whether it is your rootkit scanner, or any of these things, partially in the hypervisor, to protect it from being attacked by whatever malware infects your guest operating system. The other advantage is that with a hypervisor, you can actually introspect very early boot sequences, which typical sort of, you just have a security software that comes in as part of your boot sequence after a few other things, then the early boot part cannot be monitored by the typical security solution we install. Whereas that can potentially be examined by a hypervisor. Sort of going further, actually sitting in what you can do is, since now you're running over a higher abstraction layer, you can actually do, many of the hypervisor vendors offer you ways through which you can actually, sitting in one security appliance, monitor what's happening in another guest OS. So for example, okay, there was, potentially you can say, okay, here was a system call that happened in guest OS 1, and if I want, I can get an event in my security appliance saying, oh, here is a system call that happened, and should I allow it or not? Of course, you are transitioning many contexts, so you will be, if you do a lot of this, there will be a overhead in terms of performance. But you can use that sort of separation of domains to actually remotely do fine-grained control of certain transitions in your guest OSs. So this is sort of pictorially trying to capture the same thing, and well, illustrate this with something small we ended up building. So the idea here was that, for example, if all you want to do is antivirus scans, and actually the same ideas apply. Antivirus scan is just an example, but if you want to do HIPs or firewalls or any of those things, the same approach fundamental approach would apply. But let me illustrate it with the case of an antivirus scan. So normally what you'd have is, you have all these different guest OSs, and each of them would have their own antivirus agent. And every time a program tried to launch, you would run some scan engine, do some analysis of the code in that program, and then decide whether to permit the launch or not. Right. Now, what does that mean for you? In a typical scenario is that you end up having so many distinct copies of your same software. Each copy has to be kept up to date, which is a management nightmare. It has to keep scanning, and since scanning is a fairly expensive process, it can end up consuming a significant part of your hardware resources, right? Plus, since there is the on-launch scanning, and then there is the sort of just regular overnight scans that these guys all do, what it can also do is, if all the scans start together, you can get IO storms in your data center. So you have to at least randomize the scanning. That's the most obvious thing to do. It doesn't require any. But you have, if you don't even, look, people started and then they suddenly discovered this is the problem. Right? So the moment you transition to this kind of infrastructure, also these kind of things come up. So our idea was the following. Well, why do you need a heavyweight antivirus in each of these guest OSs? Just put a small driver which does the interception. So it will intercept the start of an access to a file, then validate whether it needs to be scanned or not. If it needs to be scanned, it will ship it over to one dedicated security appliance. Okay? And the security appliance will do the scanning and give you back a okay, not okay kind of event. So this is a very simple, straightforward way you can get a benefit. Now the question is, can you really get a benefit? What are the benefits you get from it? So sort of the example I've showed you, and I'll just go deeper into that. I'll just show you some numbers that will give you. So we did this we actually implemented something like this. And this was done actually since as mentioned, I do have a small relationship with McAfee, so we did it there, so with their products. So, and they have actually launched a product out of this called McAfee Move, optimized virtual appliance, this thing, with the Citrix people, they have done something. Okay. So the idea, example here is you have VMware ESX server, and the same thing actually applies with Zen, we have done it with Go. You have a bunch of virtual desktops, you have lots of Windows XP images being launched, and of some data store. And what you're doing is you have this sort of small agent in each of those, guest OSs, and you have one dedicated security appliance. And what we found is, for example, that if you ran 60 VMs, 60 machines on a certain particular configuration, then you had, if you were doing it vanilla, you had a certain CPU usage. If we did just this additional thing, we could run 130 rather than 60 with the same kind of number. CPU utilization has only gone up 8 to 9%. The login time has gone from 31 to, it remains 31 seconds for any individual user to log into his machine. So at a comparable performance, and of course there's a workload model here, you sort of generate a workload for each of these 60 or 130 machines, and you see that you are at least able to do slightly over more than 2 times the performance. And in fact, this is some early results, we feel it can actually go much further. And so if you look at this average request processing time number, that is basically the time. So let me go back here in this picture and try to explain where the win can come from. See, so first obvious thing is, the negative is, if your file tries to launch, you are now pausing the launch. Like, sure, you were doing a scan and you were pausing it, but that was all local. Now you have an external thread which is trying to do a launch. Like you have an IO request packet sitting somewhere, you stop that. Now you're going to do a TCP/IP. In our case, we use TCP/IP to communicate, because right now we didn't have a dedicated channel through the hypervisor. If you have it, you may get higher performance. But so we just do a TCP/IP request to these servers. So you're then sending a request, then you have to wait for the answer while the server does the scan. And it could potentially delay the launch, in addition to all the race conditions you have to worry about. That while you're waiting, what happens, what if there's a timeout, all of those things. So it could delay the launch significantly. Well, the trick is, it's a traditional computer science trick, use caching. So first thing what we do is, when we take the file, we do a checksum. Right? And that generates a sort of, if the file has a checksum, then we can just check if a file with that same checksum has recently been scanned, and if it has and it has succeeded, then I don't need to do anything more. I don't really need to get this scan. If I maintain a cache of all the files recently scanned, the checksums of those, and I just do a quick lookup on that, that can get me a benefit. Now, if you think about it for a minute, you realize that if you are in a cluster of 60 machines, really if the file gets scanned in any of those 60 places, if that information can be percolated to the other 59, that here is a checksum file that this checksum was okay, then the other places don't even have to, they don't have to do a scan at all. If you look at a normal deployment, 60 desktops would each do their scans. Now you're saying that they can start doing statistical multiplexing of their caches. They can share the information in their caches. And the way you do it is, periodically the server, whatever scans it does and whatever data it collects, it propagates it out to all the clients that this is my current value of the cache. The cache is not so large, you can easily ship it to all of them every few minutes. Right? And that gives you a huge performance. Plus, of course, so now of course what we did was the simplest case here. Offload common functionality shared by multiple virtual machines running on the same physical machine to dedicated virtual appliance on that particular hypervisor itself. But there is nothing preventing you to offload it to a separate physical or virtual appliance on a separate hypervisor, as long as you can get the request response to happen reasonably fast and your caching works. Right? So there is a lot of potential for optimizing this. You can have at least the whole rack share just one scanning machine. If you bring the hypervisor in so that you take some of the functionality that is very critical and stick it to the hypervisor, there is a plus minus to that. You may get higher performance. You may make your hypervisor more complicated, so potentially more insecure. But that's the direction you could go in. You could try sticking things much more so that you don't really need an agent at all on the guest. Some, at least from the operations perspective, people are very happy if they don't have to deploy an agent. Right? If the hypervisor can somehow have this embedded in, it seems cleaner from an IT perspective. I'm not sure that it is necessarily the right thing to do, because the hypervisor does get more complicated. But it's a thought. Other issues with this kind of approach is, so now we have replaced scanning by computing checksum. So every file that gets accessed, every time it is accessed, I have to compute a checksum again. Right? And which means walking through the entire file, which could be expensive. The first question is that more expensive or scanning more expensive? So we did some measurements with the typical set of files scanned at root and login, and we found that MD5 turned out to be 3 times faster than a regular scan. With the particular wireless product we look, but sort of a regular scan seems to do much more, whereas here you're just doing a very fast this thing. And of course, this part is just a computational performance, and the time to populate the cache is a separate cost here, because if you go to walk through all of it, it could be a positive if the file is about to be run and your cache gets populated already. Then at the time the file runs, by the time the thing runs, you may actually see the thing running faster only. So it's a far more complicated interaction. And at least for very large files, if your files are like 100 megabytes or above, then scans don't really look at the whole file. Typical wireless scans look at the prefix or log, and then they pick which areas to look at beyond that. Right? So, for very large files, this may not be very, very efficient. But then the number of such large files are typically small, so it works out. I already mentioned about the fact that the cache gets propagated to others. The other subtler issues, so if you start shipping the cache to everybody, right, then how do you keep your LRU data, like cache usage data? If a hit happens, it happens at the local guest agent. So how does the central server know that what is getting hit a lot? So that information has to percolate up. So you have to have a periodic sort of usage statistic being shipped up so that you can do your aging of the cache properly. In validation, see, things are running for days on end, right, with desktops or this thing, and you may have a data update every day, and then suddenly something which was okay last time is no longer okay. So you have to flush. The simplest obvious solution is reasonable as a starting point, as a strong at least, that every time you get a data update, you have to flush your cache, assume everything is again, has to be scanned again. Also, there is issues like, okay, while the data update is going on, what do you do? So these are, the solutions are also fairly straightforward. So you first of all anyway need not just one server, but for high availability and reliability, you need 2 offload servers so that you can go to one or the other. And you can take one offline, do the data update and bring it offline. So that kind of things are parts of the problem you need to solve there. Another interesting point is, you are not saying this is the file I was trying to access. That file I am now giving it to the security appliance to scan. But how does the security appliance access that file? See, that file, what you have is a file handle, which is translated in that particular user and processor's context. And there you have the credentials to access that file. In this case, you may not have the credentials. Right? So what do you do? Well, one option that originally we suggested was, well, okay, this is a special appliance anyway. Make him we were doing this, at least in the beginning, make him a domain admin and give him privileged access to everything, which is a open, and it turns out that that is something nobody wants to do, but just stick domain access credentials into this appliance and then create a whole one. So what we did is we said, well, it's actually simpler. What you can do is, I can do the read and transfer the first 64K of the file in one go when I send the request on my TCP IP connection itself. And then, subsequently, any parts of the scan, it asks for, you just do a simple get put kind of thing. It needs this segment of the file, you transfer it. It's a simple, sort of very trivial file system call implementation. Nothing. But, so you need to do things like that. Of course, VMs tend to get migrated. That is their claim to fame. So, what happens when you migrate a VM? How do you select the new offload server? So you need lots of offload servers. You need an auto discovery mechanism for offload servers. And finally, all of this doesn't really address the fact that, you see, even this agent doesn't, so this is coming in when my agent comes in when the system boots up. So it loads it somewhere in the Windows boot sequence, but it's not checking the boot image or the what happens early on, which you can do offline. There are a lot of tools which will do offline scanning for VMs. So when it's not even running, you can scan it. Okay, so that was one example. How much time do I have? 5 minutes. I think I will be done in 5. Okay, so this one is more, that was more, okay, it was McAfee, so they wanted a product, right? It was much more, actually there are beta users right now using that, so it's, this one is more speculative. The point is, once you are doing virtualization, you can do very tricky things. What you can do is, really you're running a set of things. The actual running sequence depends only on the asynchronous events in there. The rest of it is deterministic. It's only the asynchronous events, an IO interrupt, a context switch, things like that, that changes. So if you start recording some of that, it turns out that you can do the following, for example. You can replay something. You run something, it doesn't work, you roll back and repeat. Right? So, for example, this is mostly a work of our colleague, Saurabh Bansal. And for example, what you're doing something, just to illustrate, suppose you want to do a simple critical section kind of thing without any critical section. Right? Well, without any formally declared exclusion variable. So you have debit equal to 0, credit equal to 0, and transfer does debit minus minus, credit minus plus plus. And you want to assert that debit plus credit will always be equal to total. Right? If you have a race condition, this may not work. Right? So these are this is the critical section. That's the shared variables. And here is the critical section, which would normally fail. And in this case, what actually happens depends on the sequence of context switches. So suppose you run this, and then suddenly you get an exception of an assert failure. It comes back to the hypervisor. What does the hypervisor do? It can say, okay, I tried to interleave these two instructions, and that didn't work. So maybe I should take these two instructions, treat them as a group, try not to interleave. Okay? And rerun the thing. Back it up, so you need to do some checkpointing here, and rerun it. What can be done is, and we should, that using this, your hypervisor can actually learn what are the portions which cause problems to yourself. And so you can get the thing to run without with hardly any performance penalties. And so this kind of an approach, if it could be scaled up, could be very interesting. Use of again, of course, I'm not suggesting that we actually not use critical sections, but one of the challenges with software bugs is that with too much asynchrony, it's sometimes not possible to test every race condition or every sequence of events. And if you can just roll back and replay that somehow, that could be a software recovery mechanism. And this is some numbers of what was achieved. And there's a technical report which gives all the details of this. I will stop there. There is the other part which everybody knows, and I think the panel tomorrow will talk about it, the whole issue of data integrity and privacy in the cloud. It's an enormous topic in itself. And I will let the panelists tomorrow spend time on that. I will just stop here.
Any questions?